Am I audible at the back? It's fine. Yeah, so I think we can start. So I think the audience is the same, the one who attended the workshop and the ones who are here. So we already had a look at SymPy, what SymPy was. SymPy is a computer algebra system. So now the SymPy team has been developing on something else called SymEngine, which was previously called SymPy. And I'll talk about why it was done and uh, what SymEngine is all about. If SymPy is already a big deal, why do you need SymEngine? And how does it interact with SymPy and why is it needed? So I'm Sumith, I'm from IIT Bombay. So we already had a talk before. So what do I have for you? I'll basically talking about SymPy and SymEngine. And we'll go one level down and I'll be talking about Python wrappers to C++ code. And once you know what SymEngine is, you'll understand why all these are needed. So we have already seen about computer algebra systems. They are basically the systems which do symbolic computation. And we have seen the difference between symbolic computation and numeric computation. And by the nature of symbolic computation itself, you can understand why symbolic computation will naturally be more heavy than numerical computation. Finding an indefinite of a function is naturally more heavy because you'll have heuristics implemented. You don't know expression what to do. First you try one thing, then you try the other thing and all that sort. So that's heuristic. So basically, by the very nature of it, symbolic computation is more heavy than numeric computation. Plus now symbolic computation is no longer a subset of scientific computing. So symbolic computation is nowadays used in areas like cryptography, artificial intelligence. Now there is a huge base. So not only scientists use, there are many other people using it. So the one thing is there is a huge demand. Plus the algorithms are pretty heavy. So by the nature of it, you need them fast. So that's why you need them fast. Even if you implement the best of algorithms, at the end of the day, when you are working on real life problems, they turn out to be slow. So there's always a need to make them faster and faster. So we have seen SymPy. SymPy is a pure Python library, and we know that Python lags in performance edge cases when you have very complicated algorithms implemented. But what we like about Python here is the interface. We love using Python and we love doing computations when the language and the syntax is Python. And things are pretty simple. We have already seen this. So things like calculating Laplace transform is just one line of code. And we have seen all of this. So how we differentiate and integrate expressions and solving equations and all that sort. So people who were not there at the workshop can just have a look. This is how simple it is to actually do computations in SymPy. It's just a Python functions to call. So SymPy has developed over the last 10 years, and we have multiple modules across all areas. And they're like pretty much almost all the things that a computer algebra system needs. And we embrace Python in the sense that everything is written from scratch with Python. There's no dependency at all. So then, what is SymEngine? Let me talk about that and why we needed SymEngine. So a group of developers of SymPy, they branched off and they started developing the whole core of SymPy in C++. The basic idea is the same data structures and all that, but still you develop them in C++, and by the very nature of the language, at the end it will be faster. The only trade-off is the development time. To develop something in C++, it takes a lot more time. That is something if you have programmed in both the languages, you would have already experienced. So in Python, once you have the idea in mind, converting it is pretty simple. So, but in C++, it takes a lot of time to convert something into code. So there's a trade-off between it takes a longer development time, but at the end you have a faster system. So what we did was the team, they branched off. They started developing the core, just representing a expression, mathematical expression that was initially built. So we built the core in C++. So why was this needed? So SymEngine is basically a computer algebra system which is again written from scratch with no dependencies at all in C++. There is one dependency which is a big integer library, since C++ itself lacks a big integer library to represent huge numbers. So there's one dependency on GMP library. Other than that, SymEngine is written from scratch in C++. what was the need? Python was too slow. We had implemented the best of algorithms. Still, some use cases it turned out to be slow. So, but again, there's one thing that SymPy is already developed a lot. So you don't want to reinvent the wheel and implement whole of that again. And we love the Python interface. So what the whole idea was, just build the core in C++, and then you use Python wrappers to that. And once you use that, you can execute the code from your Python console or your Python code. So that's the whole plan. So if you have attended the workshop, we did it in 2 stages. First, we constructed the expression, then we do manipulation on the expression. So you can think it in this terms. Now till where SymEngine is developed is, you can construct the expressions in C++, and you can do SymPy operations on that. So that's why it's pretty fast. So the expression, so the core is very fast. So when you do operations on that, so basically all the modules that SymPy has already developed is still in use. So since you have the core, you can call some other module on that, and then the things turn out to be faster. So if you we actually benchmark it so that now the target of SymEngine is, there are multiple computer algebra systems already out there. So the whole target is SymEngine to be the fastest computer algebra system out there. If there is anything else which is faster than this, then there is no point of developing this, right? You are again building one, there is something else coming up. So every time whenever we develop something new, we see to it that we are keeping it as fast as possible. So SymEngine is again a fast symbolic manipulation library built alone in C++. And doing computation on SymEngine will look like this. You will have C-style computation. You have to define data types and all that sort. So this basic is a basic expression in SymEngine. So whenever you do something in SymEngine, you have to define data types and all that. And constructing expressions, again, you have to pass functions and all that. Right? This is C-style. You sacrifice your comfort to gain speed. But again, we have wrappers to SymEngine. Basically, what it does is it takes your C++ and it's called from Python. So hence, the SymEngine core has a Python wrapper on top of it, the Python console. So what you see here is basically calling SymEngine from Python, and this looks very much like SymPy, right? So basically, if you do this is SymPy, and you can, if you import SymPy and if you do operation on SymPy, that works. So that's the whole point, and it will be faster than what it would have been if you would have used SymPy expression. That's the whole spirit of SymEngine. And the basic, and still, since SymEngine is still in development, early in its development stages, we have not much implemented, but we have some considerable huge modules implemented. So these are some of the functions. This comes from the number theory module. We have prime factors, quotient functions, and all that. And we have a very good matrix module. That was one of the first things that was implemented, because many other modules will depend on the matrix module. So matrix module was one of the first modules to be implemented. So all these functions, if you see, they are very analogous with the SymPy. So if you know to use SymPy, just if you change the import, if it's implemented in SymEngine, the same functions go through. So again, what's the plan for SymEngine? Write the core in C++, and then you can keep it as an optional core to SymPy. So you can choose if you want to use SymEngine as a SymPy core, you use it, it'll be fast. And again, if you know about Sage, as I also said in the workshop, Sage is one computer algebra system which has many computer algebra systems in its background. And if you call something, if you tell it to do some operations, it will call the respective computer algebra system. So the one more aim of SymEngine is to make Sage use SymEngine. It already does. So if you are using the latest development version of Sage, it uses SymEngine as a symbolic engine. Previously, it used to use something called Gynax, and now SymEngine is faster than that. So hence Sage uses this. So eventually, what do we want to do? Since SymEngine is just a core, we want to not only Python wrappers, we want to develop other wrappers to it, Julia wrappers and MATLAB wrappers and all that sort. So that whenever you are using it, whenever you are doing some computation in that environment, you can take advantage of SymEngine from that. So that is the eventual goal of SymEngine. SymEngine to be that one fast core that everybody can use. So that is the whole spirit, and we want it to be the fastest. So nobody else has to again go through the whole process of building a computer algebra system from scratch. So now let's go one level deeper. Now I said SymEngine was wholly developed in C++, then how do you call it from Python? So the problem comes down to this, making Python call C++ function. So we have a C++ function or the file, we need to use it from Python, and the interface is, and there's the interface that comes in between. So there are multiple things that Python itself has a Python C API which allows you to do this, but it's pretty messy in the sense that if you actually go through it, you'll have to construct objects, and it's not actually built for converting a whole C++ library to Python. There are multiple other things. There's Swig, there's Boost Python, F2Py, and there's like multiple things which actually let you to interface Python with other languages. And there's something called Cython. So what we use in SymEngine is Cython. So I'll talk a bit about Cython. So how SymEngine does it is, Cython is it uses Cython. So Cython is a blend of Python and C. It takes some spirits from C, and hence at the end of the day it actually improves performance. So there are two ways of using Cython basically. Cython, one way is you can think of it as a language source. You can code up things in Cython, and you can use it in Python. You can what it basically does is you can write a Cython code, and you can compile it, and what it gives you is a SO file, and you can import it from Python and you can use the function. And the other way of using Cython is there is a C++ file, and you tell Cython take this function to that C++ function, and that's called wrapping. That is other way of using Cython. So we'll see both of them. So this is one basic example where Cython comes in between. So if you know Fibonacci numbers, this is an example of that. So in Python, calculating Fibonacci numbers would be this. There's a for loop, and in C++ it's pretty much the same. So it's not much different. And the Cython code looks very much like Python code, but there's just one difference if you notice. There is before the data types you write cdef int. So that is actually contributing to the speed. Whenever you do this in Python, right, a comma b equal to 1 comma 1. So you are not actually mentioning the precision of the data type. So a can be as big as possible. But when you do this in C++, say it's int a comma b, you are telling it that it's limited to this much bytes. So that actually contributes to the speed. In Python, at any point in time, if you multiply this by a very big number and if you put it back in a, it works so. But in C++, it doesn't work so, and that trade-off contributes in the speed of C++. The whole idea of if you compare these two codes, if you take it as 1x speed, this C++ code is 100 times faster, and the main reason for speed is this data type, because you are limiting the data type, hence it knows how much to allocate, and it doesn't have to move the allocation. In Python, if you something huge, you'll have to move the allocation to somewhere else. So the main contribution to speed is that. So basically what Cython is doing is it's taking the code looks the same as it's in as in Python, but it's just telling the data type, and that contributes to the speed. And it's 80x faster, which is good enough for us. Right? If you are writing code as you are writing in Python, and you are still doing 80 times better, and that's good enough for us. So this is one way of doing it. And there is other way of doing, as I said, there is a C++ source file, and you're matching Python functions to C++ functions. So basically what is happening is there's a Cython source file called .pyx. The Cython source file, it generates an equivalent C code, and that equivalent C code might be pretty huge because it's generating from the Python code, and then that is converted to an extension module, and that you can implement from that you can import from Python. So this is how it looks. So if you have a string length function which is defined in string.h, your Cython code will look like this. You have to import that function, and you have to tell that the getLength function in Python returns the string length of the C++ function. So whenever you import this module in Python, the string length function is not there, but you can call the getLength function, which is actually this Python function, and you will get the answer. Fine. So I have a few examples that maybe we can try out. let's see. So I have a Cython code. What it's doing is, I'll show you an example. So there's a Cython code. What it's doing is, it's called pi square add. What it's doing is taking two numbers, it's taking its square and adding a floating point to that. And this is Cython code. And we'll test it. What we'll do is we'll write a similar Python code, which is called pi square add. And it's doing the same thing. And what we'll do is we'll execute this, and we'll execute the Cython code, and we'll compare the timings. Okay, fine. I hope you get, there's a very simple function. We are doing that in Python, we are doing that in Cython, and we are comparing the timing. So basically, before you do Cython, you have to compile the Cython file. So once it does so, we can, I think, test the file. So let me increase the font size. So is this clear? Is this font good? Yeah, so you can see the timings here. Is it visible? Yeah, so the Python, even a function as simple as that, times 0.23 seconds in Python and times 0.070475 seconds in Cython. So that's where the speed difference is at. So again, coming back to SymEngine, we are a very small team as of now. Again, Andre started this project. His idea was, whatever now about SymEngine and all that was his idea in the beginning. And we only have so many contributors as of now. And there are like a couple of names more that just came in last week. So, and now what is there in SymEngine is we have the basic core there, and we have the matrix module, function module, and number theory module. And polynomial module, there is polynomial module has been implemented till the univariate, and multivariate is still being implemented. And on top of that, we are now working on series module. And we have had 6 GSOC students in the past 2 years. We'll be having many more in the coming year, since we have much more work to do now. And we had the first beta version recently in October. And the immediate goals would be completing the polynomial module, extending it to the multivariate case, and series expansion and pattern matching. Eventually what we want to do is, we want to do assumptions. What is assumptions is basically, whenever you declare a symbol and whenever you do operations on the symbol, what SymPy assumes by general is that symbol can be anything. By anything I mean, it can be real number, it can be complex number, it can be anything. But if you already know beforehand that symbol can take only positive values, symbol is only real number, by default you tell SymPy that do the operation such that symbol, and then things might simplify. So things of that sort. That's pretty complicated actually. It's not as easy as I'm saying it to. And that's our eventual assumption, to have assumptions in SymEngine itself, since it's a very high overhead, and that actually slows down things. And we as any open source organization, we would want a huge community as big as SymPy. SymPy has 400 contributors now. So something of that would be pretty cool. So to summarize, what I thought was basically symbolic computation, SymPy and SymEngine, and how they are related. They're related, and the interface lies in Cython. And I would like to acknowledge Kurt Smith and for his some of this material that I've used. The example that I've taken is from his SymPy 2015 talk. So I hope you enjoyed. So that's all I had. I hope you understand. Hope you can take home the whole spirit of SymPy and SymEngine. So there are a couple of people who were asking me yesterday how to start off with the SymPy and the SymPy contributions. So I'd like to show a bit about that. So my GitHub is I go by the handle Sumith 1896. So you can SymEngine repo is /SymEngine /SymEngine, and SymPy is SymPy/SymEngine. So what you can do is you can actually join the mailing list, and you can actually join our chat room. So any and every questions are answered. So we are a very welcoming community. So you can either join the mailing list, and you can if you need substantial information on anything, I would suggest you to put a mail. Else you can drop by the chat room. And we also have SymEngine is pretty much goes in the same spirit. So if you want to drop by the mail, so you can do in the same. And if you want to talk, you can come to the Gitter channel. So that's it. If you want any help, you can personally ping me on any pull request or something of that sort. But there are always people to review pull requests. So that's all. Thank you.
One question. Any questions? Whoever's the next speaker, you can maybe start setting up.
Hi. Can I have this SymPy engine work with the PHP as well?
No, as of now, I don't see it. What would be? Its answer is no. But what would be the use?
So, basically, currently I am working on an application, web application, where it requires certain logical this analysis, and for that I am using Python. And by any case,
Python there, I think you can use it off that.
Yes, but it is like it seems as a separate application, not integrated application. So it is like instead of directly calling you, I have to call someone else, and he will route the request to you. So kind of an API or this engine can be directly integrated with PHP. As you said, it is.
So if you have Python code anywhere, and if you are using doing computations on Python, so it's basically a Python library. So anywhere you can, wherever you are using the Python library import, you can use SymPy import.
So currently I am doing the same way,
yeah.
But is there any integrated way, like the plugins?
As of now, if you are asking for doing it directly from PHP, I don't think there isn't.
But SymEngine has a C++ API?
Yeah, SymEngine has a C++. You can
wrap it with Swig.
Yeah.
Swig supports
Swig
PHP.
You can do things of that.
But you don't have anything currently. Okay. Thank you very much again, Sumith.